Hello, this is Taimur, and you're watching IEEE VTS Young Professional Seminar. And today we have really interesting speaker. I'm going to introduce the speaker to you in a bit. I would like to just give a brief overview or a brief background of the topic for today. So channel sounding or channel modeling and channel measurement, these are different terminologies that you hear when you look at the research papers, when you look at white papers and a lot of other materials about the wireless communication. And like most of the people who have worked with the channels, they know that it is really a non-trivial thing first to sound the channel or measure the channel and then make really practical models out of it. So it's something really tricky, and then it sets the base for our wireless system designs later on and for their testing. So today our speaker will speak about terahertz channel sounding. So you can say that it's a challenge on its own when we move into the terahertz. And then he's not only working with the terahertz, he's working with the railway. So that's another high-speed variable added to it. So for today we have our guest, Professor Kikon. I would like to invite him to the stream. Welcome. So do you hear me?
Yeah. Yes. Hello, Taimon. So, should I introduce or give some?
Yes, please introduce yourself, and
okay.
The floor is yours.
Okay, thank you very much, Taimon. So my name is Ke, full professor from Beijing Jiaotong University, and it's my great honor and pleasure to give this talk on the platform of Young Professional Committee of VT Society of IEEE. So thank you very much, Taimon, to invite me to introduce this story about smart real mobility enabled by terahertz communication in the era of 6G. And of course, the topic and focus today is about channel sounding and characterization. Yeah, of course, because when you talk about any new wireless communication technology, the baseline is to explore the propagation and wireless channel properties. This is the fundamental of the evaluation and design of the system. So we can start. As you can see, the outline, first I will introduce the motivation of smart real mobility, why we are trying to use terahertz, because everybody knows that it will be very challenging to make terahertz communications mobile. But actually, as high-speed railway, we really have some use cases that we need to explore the possibility of using terahertz for communications. Then I will introduce challenges and new paradigm for terahertz mobile channel modeling, including channel sounding and retracing. Then I will give you some examples of the terahertz channel characterization for intra-wagon scenario and inside station scenario, which are the two of the 5 smart real mobility scenarios. And last but not the least, I will give the conclusion and also outline some potential research trends that we can probably follow in the future. So first is motivation. As you can see, already this is not a new story. Actually, in the already past Horizon 2020 program, as one part of the objective of smart, green, and integrated transport, railway is already highly expected to evolve into a new era of smart real mobility, which is defined to achieve optimized mobility, higher safety, and lower costs. So here you can see 2 figures, and you can see 2 figures. So this one is actually from the company which is called AROP. So this is about the future of the railway in the year 2050. As you can see here, actually almost all the objects are wireless connected, not only from the train to infrastructure, but also from the train to the UAV, from UAV to UAV, and from train to train. And this another picture actually is a vision of the future railway from Deutsche Bahn, so from DB, Germany. So as you can see here, which is not only about the communication between train to infrastructure, but also from infrastructure to the passenger user equipment, and there are some UAVs and other parts. So that really what you can find from these two pictures is that in the future, there will be a strong need to build seamless high data rate wireless connectivity in the use case and scenarios of railway. Then the question is that how many propagation scenarios or how many wireless links that we need to research about future railway communication. So around 4 years ago, in the framework of Alexander von Humboldt Research Fellowship, in the year 2016, we launched a project regarding this millimeter wave and sub-millimeter wave MIMO mobile ultra broadband channel enabling smart railway mobility. And in this paper, we first defined the 5 propagation scenarios that we need to characterize for smart rail mobility. They are train to infrastructure and intra-wagon and intra-wagon and inside station and infrastructure to infrastructure. So we think that if we can successfully characterize these 5 links, then we will have some big picture or the whole picture of what will happen in the future for the smart railway mobility using high frequency bands. So let's see why we need terahertz bands. This is mainly because that in the smart rail mobility scenarios, high data rate applications are already required. For instance, you can see this onboard and we-side high definition video surveillance will be needed in the scenario of T2 train to infrastructure, inside station, and infrastructure to infrastructure. And also this onboard real-time high data rate connectivity is required for train to infrastructure, inside station, and train to train infrastructure, and the passengers inside a wagon. And the same, the other bandwidth extensive applications can also be found in these 5 propagation scenarios in smart rail mobility. So we can find that not only business, we need these high definition video streams for the passengers on board, but also we need these high definition video streams for entertainment. So in total, dozens of gigahertz bandwidth will be required. And this is the reason why we have to explore the possibility of using higher frequency band like millimeter wave and sub-millimeter wave, because in that frequency band we can have rich unexplored spectrum resource. So then let's see what is the challenge that when we talk about channel modeling for higher frequency and high mobile channel. So we can review that when we were in the sub-6G channel in 3G and 4G era, at that moment, for instance, if we need to do the channel measurement, channel model, we need to certain sample space, including the Doppler domain, angular domain, polarization domain, delay domain, and loss domain. But at that moment, with some capable channel sounding solutions, it is easy for us to have this full dimensional channel information from the channel sounding campaign. So with this information, we can do the channel parameter extraction to form some empirical or stochastic channel models. Then we just need this measurement samples to validate the models made based on the very rich channel measurement data. And this is also the same for the stochastic channel models. And then when we talk about millimeter wave channel in the era of 5G, so we still, in this circle, we still need this sample space for the channel modeling. But then we find that actually with millimeter wave frequency band, it would be practical for us to measure propagation loss, delay spread, and also polarization. But since there is high propagation loss at high frequencies, so usually we need to use highly directive antenna. Then we will lose the information from the other angle of arrival, or we just need to use a scanning measurement mechanism to have this full angular measurement, but then we lose the ability of measuring a dynamic or mobile channel. So that when you can see that it will be very difficult to cover both angular domain and Doppler domain properties of the channel at millimeter wave frequency band for 5G. So at that moment, more and more researchers started to use this limited measurement data to calibrate retracing simulator, and then to use the retracing simulator to do extensive simulations to extend the limited measurement data to cover the angular property and Doppler property of the channel. Then use this full dimensional data or full dimensional channel sample information from extended by retracing based on measurement data. Stochastic model can still be characterized and validated. So this paradigm still can work for the millimeter wave channel in 5G. Then when we talk about even terahertz for 6G and with mobility, then you will find that due to lack of channel sounder solution which can cover terahertz, large bandwidth, and high mobility, actually it would be very, very difficult for us to have measured data of terahertz channel, especially with mobile channel. So that we will have very, very limited measurement data. So it will be found that new paradigm is needed. So because we can, later on I will show you some measurement data that we got at the terahertz frequency channel measurement campaign, which is way less to make the channel model directly on it. Okay, so we proposed a new paradigm for channel modeling, which is with the core of retracing, not the core of measurement directly. So first, we need to define the target scenario with different parameters like the attribute of the link, which is fixed or mobile, the velocity of users, lamp side, non-lamp side, weather, scatterers, and so on. Then we can, according to this definition of the scenario, to make this 3D model reconstruction for a target scenario. Of course, this is only for the geometry, and in order to trigger retracing simulations, we need to have this electromagnetic property of the material, so that we just need to find the samples of the material that is in the target scenario, and then we can do this scanning measurements using VNA and to regress permittivity, conductivity, reflection coefficient, scattering coefficient, and exponents, and so on, to form this AM property library of the material. Then, with accurate information of geometry and electromagnetic property, we can trigger retracing simulations to have extensive simulations with different setups. Then we can have a lot of arrays with different attributes or different propagation mechanisms like reflection, scattering, and diffraction. So of course, we need to identify what are the major propagation mechanisms in this scenario, and then we can make the hybrid channel model based on this information. For instance, we can use some parameters regarding geometry information to make the hybrid channel model spatial consistent, and then we still can use some random variables to make the channel stochastic enough. Then using this stochastic or hybrid stochastic channel model based on extensive retracing simulations, we can realize the channel properties at a high speed that we cannot measure in reality. For instance, this is a power delay profile of a millimeter wave channel at the speed as high as 500 kilometers per hour, and this is a Doppler spectrum. So you can see that actually all these multipasses can evolve smoothly. So this is so-called spatial consistent, which can overcome the limits of the purely stochastic channel model in the past. So with very small amount of data, we can validate the channel model, which is based on the retracing simulation. So we proposed this new paradigm and published it in the IEEE transactions, received awards. So if you are interested, you can see more details in this paper. So for the terahertz channel modeling, the new paradigm is also used. And this time, first, we only do a small amount of channel sounding like this. So here, and then based on the channel sounding, we can validate the retrace and do extensive simulations. Then with rich and full-dimensional channel data generated by retracing simulations, we can do stochastic channel models for each of the major propagation mechanisms. Then we can do channel realization and validate it with the limited channel measurement data. So then let's go to more details about each step of this paradigm. So first is about channel sounding. Actually, there are different methods of doing channel sounding. So here, what I would like to introduce is a time domain channel sounding based on sequence, or based on sending sequence and doing cross-correlation. So the advantage of this time domain channel sounding solution is that you can capture all the frequency points at the same time, so that it will not be so slow like doing frequency scanning measurements using vector network analyzer. So this is an advantage. So as you can see here, the transmitter will transmit a pseudo-random binary sequence, and then at the receiver, since we have the received signal and we know the reference signal, so we just do the cross correlation. You will have the channel impulse response like this. So since you know that this channel sounder working at ultra broadband, which is 8 gigahertz bandwidth, so that there will be a need to use this central clock source to have this phase recovery for the receiver side. So this channel sounder is not able to really measure the mobile channel, but since we can capture all the frequency points at the same time, it can measure dynamic channel but not the mobile channel. So that in the scenario there could be some other mobile scatterers around, or like passengers, but the transmitter and receiver will not move about by itself because they are connected by the cable to the clock source. Okay, so this is what it looks like. So it's 9 gigahertz base IF. And we have 2 frequency extensions at 60 gigahertz and 300 gigahertz, and the full setup is up to 424 MIMO. And this is how it looks like. So as you can see here, since at terahertz band we have this highly directional antenna, then we need this rotation unit to realize mechanical horizontal scanning. And this is a UWB transmitter, and this is 300 gigahertz frequency extension. Okay, and we did some test measurement in a classroom, and like this. So there's this horizontal scanning happening here. And then let's see, this is a measured angular domain, angular power spectrum with vertical polarization in the room, and this is a simulated result. And this is for the this is vertical polarization, and this one is horizontal polarization. So you can find that actually really in the terahertz frequency bands, actually the channel is quite multi-pass sparse. So it's not a lot. There are not a lot of multi-passes, but you can also see that the retracing simulator is able to perform the channel properties and multi-pass constitution quite well at this frequency band. And here you can see this is also the angular power spectrum, but you can see it's more colorful. This is because at the same location of the transmitter and receiver, we use extension not to 300 gigahertz, but to 60 gigahertz. So this also shows that with increase of the frequency, the channel in the typical indoor environment is really more sparse. Okay. And then let's go to another key technology of retracing. The retracer that we use is called Cloud RT. Here is a website which is open for global users totally for free. So now we have more than 4,000 users from 60 countries since 2018. And since we know that retracing is very computing exhausting technology, so that we built this high performance computing platforms for this retracer. So then it can be used for higher frequencies and large scale of scenario. And in this retracing platform, we have a lot of 3D environment model library, antenna library, and material library. And as the users, you can upload your own antenna patterns or interested 3D model of environment, so that the other users can also use them. So this is like good contribution to the society. Okay. So then let's go to some technical results of our work. So first, this is a channel sounding measurement at 300 gigahertz with 8 gigahertz bandwidth with directional antenna with antenna gain of 15 dBi, and the main lobe of the antenna is 30 dB. So here you see the corridor of the wagon. So as you can see, because the equipment of this channel sound is huge, right? So you cannot really put it to the space where the user equipment will really appear in reality. So this is just reference measurement. You cannot use the data directly to form any channel model, because no user equipment will fly in the sky like here, like in this setup. But this is the only setup that we can realize with this huge channel sounder. So this is the reason why I emphasize that we we can only need the or we can only use the limited measurement data to validate or calibrate a retracer, and use that validated retracer to really have extensive simulations to have the channel data which is meaningful for users and the channel modeling. Here you can see this is an angular powered spectrum of this horizontal scanning, terahertz retracing, terahertz channel measurement. Here you can see this is noise floor, noise throat, and then you can see there are some multipasses. Okay, and actually they are from different angles of arrival. Here, the Rician K-factor is around 8 dB, which is not bad since there's a clear line sight, and the arms delay spread is around 11 nanoseconds. Angular spread is not very small, which can be explained by the diverse angular distribution of these multipasses. Okay. And then we can rebuild the 3D environment of the wagon, including all the components, and then we can do the retracing simulations. Here, as you can see, these are the major rays from the first order of reflection to some higher order of reflections. So here you can find these crosses are the place of the result of the retracing. So they are overlapped to the measured peak in the channel sounding measurement. Okay. So here, this is a calibrated result of the retracing simulation against the measurement. This is channel impulse response. So here you can see after the calibration, so all the multipasses are correct not only in the terms of the power, but also in terms of the time delay. So, and of course here, as you can see, the result of the calibration actually is about the permittivity of the relevant material. This is glass and metal here. And then we can do the retracing simulations for some meaningful setups. For instance, we can put the how to see the receivers on the table, on the chairs that are more practical for real use cases. And this is one snapshot of the retracing simulation in the simulation, so that you can see there are a lot of rays, direct ray, reflected rays, and scattering rays here. And then we define 3 regions. So maybe it will be strange, because we know that line side and non-line side. So why we distinguish the non-line side into light non-line side and deep non-line side? This is actually because we found that even at higher frequency like terahertz band, whether there is a first order of reflection really determines channel properties, which means that if you do not have line side, but fortunately you have one strong reflection, then you still have almost like the line side region propagation condition. Okay, so but if you even do not have the first order of reflection, then it will be totally dark. Then we call it deep non-line side region, and you do not expect to build a link in the deep non-line side region. Okay, so here you can find that when you put the transmitter in the center of the wagon, then you have the line side and non-line side, light non-line side areas like here. And if you put TX at the side of the wagon, you have the yellow area and green area, which are possible to build wireless link, terahertz link here. So the rest is totally dark, which is with the dark blue. So we analyze that, for instance, here this is key parameters of the path loss and the shadow fading and Rician K-factor. So you can find that no matter it's in the text is in the center or on the side of the wagon, the key parameters of channel regarding propagation loss and shadow fading and Rician K-factor are really similar to each other between the lamp side and light non-lamp side. But when you talk about, when you see the values for the deep non-lamp side, it's very bad. So that we found that the first order reflection becomes almost the only chance to build the link if the lamp side is blocked. And the RT simulation results imply that the existence of the first order reflection indeed determines channel characteristics. So we made this simulation to find out how many access points will be needed to have very good coverage with lamp side and light non-lamp side areas in a wagon. So actually, you can just need to put 3 access points here, and then you will have more than 70 or around 80% of the areas with either lamp side or first order of reflection, which are good to build terahertz link. Not bad. Okay, so of course, apart from propagation, delay spread, shadow fading, we can also estimate the other large-scale parameters like the angular spread and the clustering and also shadow fading angular spreads within each cluster. So these are the input parameters for the 3GPP-like cluster-based channel generators. Here we use Quadriga. So, I mean, if you can estimate these input parameters from Rician simulation data, you can trigger Quadriga to generate stochastic channel data. Okay, that is a story about Intra-wagon. Then we move to the inside station scenario. Here you can see we also did a measurement between infrastructure to a train. This is a typical like within in a station scenario. Still at 300 gigahertz with a directional antenna, and you can find that actually the Rician K-factor is around 4 dB, not very bad, and the arms delay spread is like around 9 nanoseconds, which is slightly shorter than the case within the wagon. Then we use a Rician simulation later to do the simulation and make the calibration and validation with the measurement data. So here you can find this is a received signal power for the line side pass and reflection pass here. And the interesting thing is to find out where this super long delay reflection from. So with the aid of the Rician simulation, we can find that actually this is a second order of reflection, but the reflection point is in the inner wall of the wagon. This is because in the inside station scenario, and also in this measurement campaign, we had this gate of the wagon open. So that this is a very interesting finding that in these scenarios, when the gate of the wagon is open, it's possible for the inner wall to form some super long delay reflection multipass. Okay, then with this validated simulator, we can do extensive simulations. The first thing is to model real railway station. So maybe you can find out where it is by yourself. And then, of course, we want to know the influence of different setups of the transmitters, and whether there's another train on the adjacent track. So we define 4 scenarios. The first one is called PNT. This is when the transmitter is on the platform and there's no train on the other track. And this is the second one is PT. So the transmitter is on the platform and there is a train on the other track. And then this is a CNT. So when the transmitter is deployed on the container, is on the catenary mast between 2 tracks, and there's no train on the adjacent track. And this is CT. So when the transmitter is deployed on the catenary mast and there's another train on site. Okay, so let's see the interesting simulation results. First is about the path loss and shadow fading. So here you can find that there's a very regular fading pattern in these 2 cases. So here you can find that usually this regular fading pattern is related to Turing model. Actually, not only Turing model, but if you have 2 or some limited but strong enough reflection or multi-passes, then you have this interference regular pattern. So we go back to the simulation snapshot. You can find that here you have the long side, but then you have strong reflection from the upper from the floor of the station and also from the ceiling of the station. And this is also the situation here like this. But for another 2 cases, since there are no strong multi-passes like this, then you will find that the fading pattern is totally irregular. Here, this is a CDF about Rician K-factor. So here you find it very interesting is that for this one, you really have the line side, but you can see the median value of the Rician K-factor is even smaller than 0 dB. This is quite abnormal, right? So when you go back to see the situation, then you can find that this is because although you have line side, but you have strong multi-passes from the metallic body of the train, so that you really have a lot of strong multi-passes. So then you have the very small Rician K-factor. Then this is like the metallic corridor or metallic confined space, like tunnel. This is a quite unique propagation condition that you need to consider when you design a communication system for this scenario. So much stronger multi-passes can be received when the TX is deployed on the catenary mast, and the reflection attenuation caused by metallic train body is trivial, and therefore considerably decrease Rician K-factor. Okay, let's see the CDF of the angular spread of arrival and of departure. So here you can find this for these 2 scenarios. Actually, the angular spreads are much larger than the scenarios here. So especially for this one, you can find that for the for this situation, you will find that the angular spread of departure of this scenario is really small, but here you will find that the median value of the angular spread of departure in this scenario is quite large, like 40 degree. So here the reason why I have already explained, that is because you can find that when another train is on the another track, this another train really form strong reflections together with the communicating train. But when there's no train on the adjacent track, then you will not have this strong multipath reflections from it. So here you can clearly see the influence of the other train on site, which is to generate strong multipasses to increase the angular spread of departure. Okay. And these are the CDFs of the elevation spread of arrival and departure. So you can see that the ESA and ESD are much smaller than those in the azimuth plane. So this means that if the TX and RX are vertically polarized and with a similar height, which are relatively high from the platform or ground, most of the multipasses are actually generated on the azimuth plane, which has potential to offer more diversity gain to the MIMO system, so that you really should utilize this angular spread in the horizontal domain or azimuth domain. Okay, so still we can estimate all these channel parameters based on the extensive retracing simulation data to feed into 3GPP light channel generators like Quadriga. And this is the result between the stochastic channel generated by Quadriga and the retracing simulator. Actually, they are quite good, having good agreements between each other. This is a path loss for the 4 scenarios of the inside station scenario, and this is a Rician K-factor. So the Quadriga can generate stochastic channel data with the same statistic characteristics of the retracing simulation results. Okay. So let's conclude our talk this time. So first, we really need new paradigm of channel modeling for high mobile and high frequency channel, because there's no multi-channel sounding solution which can cover terahertz, large bandwidth, and high mobility, so that we can only have this limited channel sounding campaign and data then, but we can use them to calibrate retracer and use that retracer to do extensive simulations and realize stochastic channels. Then we have gained some insights into the terahertz propagation features of smart real mobility. First, it is sufficient to consider up to the second order of reflection for propagation mechanism constitution in intra-wagon and inside station scenarios. And even without a line-side condition, the terahertz link can be built if the first order of reflection exists in the intra-wagon scenario. So I have already explained that when you go to the details of the channel parameters, you will find that actually the channel properties of the lamp side and the light lamp side with the first order strong reflection from the metallic inner wall of the wagon, they are quite similar. But if you even do not have the first order for reflection, then you fall into the total deep non-lamp side, and you do not expect to build any terahertz link in that situation. So for the significant objects, train wagons, glass windows, and any metallic objects with smooth surface and dimensions obviously larger than the wavebands of terahertz, should be considered in the 3D model with reconstruction. And for the system design, there are some special concerns. For instance, in the intra-wagon scenario, there may be multi-passes with the same delay, but with different directions, so that you really need retracer to help you to understand the measured multipass, because when you have this power delay spread, power delay profile, you will actually have some multipasses with the same delay, but actually they are from different angles, and they are from different objects. So by using ray tracer to do simulations, you can clearly see where they are from. And then the inner wall of wagon or the door, when door is open, can reflect the multi-passes with unexpected long delay in the inside station scenario. As you can find that the inner wall actually can form this reflection. And if we do not measure it and use ray tracing simulator to validate it, so even I personally will not believe the inner wall of the wagon can generate effective multi-passes. So be careful of this phenomenon. So this is all I would like to share with you regarding the current research results about terahertz channel in railway use case. Thank you very much.
Thank you, Kay.
Thank you.
So nice to listen to your talk. And yeah, a lot of new things for me as well, because, you know, back many years back, we started with 6 gigahertz channel sounding, sure, where we had opportunity to work together for some time in Braunschweig. So I would like to ask one question in this relation, that, you know, like you have worked with gigahertz band from 3 gigahertz, 6 gigahertz up to millimeter waves, and now you're working with the terahertz. So what is the major difference that you find, and what is the most difficult aspect that you find in terahertz as compared to gigahertz?
Yes, so thank you for your question. So first, I find that the channel is really sparse, much more sparser than the sub 6 gigahertz channel. So this is what we really observed, and we can conclude, at least for the indoor or limited space, like inside wagon or inside station. Maybe in the forest, it's not like this. When you really have a lot of vegetations with leaves with the comparable size of the wavelength. But at least for this really human constructed scenarios, the channel is much more sparse. And the second difference is that I found that if you have the first order of reflection, you can build the link even at terahertz. I think this is somehow out of the or beyond of the imagination about from a lot of people, because people believe that we need line of sight. But actually, during our study, we found that if you have first order of reflection, then the terahertz channel is almost with the same property. So this means that we can have some reflectors or reconfigurable intelligent surface or something like this to generate the first order of reflection. Then we still can join the terahertz link. And of course, the challenge is really huge. For instance, as you can see, we did study for like 2 years, and we only collected this very limited channel impulse response with very limited degree of freedom, right? Correct. I either have this delay domain, then I lose the angular domain. If I have angular domain, I never have Doppler domain. So I think the challenge is that you never have full dimensional channel information from measurement directly. Then you really need some other simulation method. So
yeah, this is totally understandable. And maybe that is one reason why we see very similar results for ray tracing and measurement, because the channel is sparse, so we do not have too many second order or diffuse scattering. That makes it difficult for to reconstruct it for the ray tracer. So if you have line of sight, first order reflection, it's fairly easy to make a deterministic channel of it. So that is why we see very similar results. Yeah. Thank you. It was exciting, and thank you for taking your time to speak to us and to share your research. I would like to see you again, hopefully soon, in another seminar with more interesting results. And I would like to thank all the viewers for today. And please post us if you have any questions. And I will provide the link of Kay's research profile from the university and Google Scholar down in the description. So you can go and see all his research work and papers. And maybe if you find something interesting, you are welcome to contact to him. He has provided already his email address. So I think that's the whole point of this, that we establish cooperations.
Okay, sure. Thank you, Taimo, very much. And so as you can see, even though we have already studied for a while on this topic, but so far the progress is far less than what we achieved for the sub-6 gigahertz channel. So we really have a lot of things to do, and we really hope that the fellows or the other partners from the other universities or institutes to contribute to some dynamic channel sounding measurement result and so on. So we will be very glad to support our retracer to different users totally for free for the purpose of research and education. That's so nice. Look forward to any contact, and thank you, Taimo.
Okay. Great. Thank you for today.
Okay, thank you. Bye.
Bye.